Good day, everyone. Welcome to this week's SYNThink. I am Christian Jan Alado, VP for Academic Services. For this week, we have an integral calculus problem or call-into problem, which wants us to take the integral of the equation x squared ln of x plus cos raised to 6x sine squared x plus 1 over square root of x minus 1 dx. To solve this problem efficiently, let us first apply linearity, which means we take the integral of each term one at a time separately. So, let us take the integral of the first term, x squared ln of x dx. As we can observe, we can apply integration by parts for this problem. So, let's take ln of x for ru and x squared dx for r dv. Then, we get the differential of ln of x, and we get our v from dv by integrating x squared dx, which then gives us du equals dx over x and v equals x cubed over 3. Now, we have to multiply uv and then subtract it by the integral of v du, which gives us x cubed over 3 ln of x minus integral of x cubed over 3 dx over x. Now, we can apply the basic integration formulas for our second term. Now, we can get from the integral of x squared dx, we have x cubed over 3. And multiplying it by 1/3, we get x cubed over 3 ln of x minus x cubed over 9. Now, let us take the integral of our second term, which is cos raised to 6x sine squared x dx. For this problem, we can apply trigonometric transformation, wherein we use sine squared x equal to 1/2 multiplied by 1 minus cos 2x and cos squared x equal to 1/2 multiplied by 1 plus cos 2x. So as we know, this is from our double angle identities. Now, we have to factor out cos squared x from our cos raised to 6x, and we do that by raising cos squared x to 3, then multiplying it to our sine squared of x dx. Now, let us substitute our values for cos squared x and sine squared x from the identities that we have, which gives us 1 plus cos 2x over 2 cubed and 1 minus cos 2x over 2 dx. Now, let us take out our constants, which is rather 1/2 cubed and 1/2, which gives us 1 over 16. And let us also expand our cube, which is 1 plus 3 cos 2x plus 3 cos squared 2x plus cos cubed 2x multiplied by 1 minus cos 2x dx. Now, let us multiply them with each other, which gives us 1 over 16 integral of 1 plus 2 cos 2x minus 2 cos cubed 2x minus cos raised to 4 2x dx. With that, let us now once again factor out and simplify our terms wherein we cannot yet apply our basic integration formulas. And those are negative 2 cos cubed 2x and minus cos raised to 4 2x. For cos cubed 2x, we can apply our Pythagorean theorem for this example, taking out cos squared 2x and equating it to 1 minus sine squared 2x. And for our cos raised to 4 2x, we can once again apply our double angle identity, which now gives us 1 over 16 integral of 1 dx plus 2 cos 2x dx minus 2 integral cos 2x 1 minus sine squared 2x dx minus integral of 1/2 1 plus cos raised to 4 2 1 cos 4x squared dx. Now, let us expand our last term, which gives us 1 plus 2 cos 4x plus cos squared 4x dx. Now, let us once again apply our double angle identity for our cos squared 4x at the most right of our equation, which gives us 1 plus 2 cos 4x plus 1/2 plus cos 8x over 2 dx. Now, as we can see, everything is now simplified. And with that, we can now apply linearity once again And after that, we can apply our basic integration formulas to each of our terms. For 1 dx, we know that's x, and for plus 2 integral of cos 2x dx, we know that that is just sine 2x. And for our, apologies, and for our next term, we have cos 2x. We distribute that to 1 minus sine squared 2x. We get cos 2x minus cos 2x sine squared 2x. And with that, we can apply a basic integration formula for our sine squared 2x. And we have 1/4 integral of 1 dx, as we know again, that's x. And for plus 2 integral of cos 4x dx, we can just apply power rule.
Stop! Hello everyone, this is Editor Christian, and I'm just about to correct myself. So instead of using the power rule for our cosine functions, I instead used our basic trigonometric formulas for cosine, which is cos u du is equal to sine u plus c. So back to the video.
And then for 1/2 dx, we know that's x over 2. And then for our last one, we can also apply power rule. Now we get 1 over 16 multiplied by everything, which is x plus sine 2x minus sine 2x minus sine cube 2x over 3 minus x over 4 plus sine 4x over 8 plus x over 8 plus sine 8x over 64. Take note of our signs, wherein sine 2x will become negative, and then sine cube 2x over 3 will become positive. That would cancel out our sine 2x for our final answer. Take note also for the signs of our last term. So with that, our final answer is 5x over 128 plus sine cube 2x over 48 minus sine 4x over 128 minus sine 8x over 1024. Let us now take the integral of our third term, which is 1 over square root of x minus 1 dx. For this problem, we can apply algebraic substitution, wherein we take x equal to z squared and we take its differential, giving us dx equal to z dz. Now we substitute our values of x and dx to our original equation, which gives us integral of 2z dz over square root of z squared minus 1. Canceling out z squared, we have 2 integral z dz over z minus 1. And factoring out the equation, we have integral of 1 over z minus 1 multiplied by dz plus dz. Now we can apply our basic integration formulas, wherein for our first term, we can apply logarithmic, and then for our second term, it's just a constant. Now we have let u equal to z minus 1, and our du here, differentiating this, is dz. With that, we can now have 2 ln of absolute value of z minus 1 plus z. However, as you know, z is not our variable, meaning we still have to substitute x back to our equation, wherein z is equal to square root of x. Now, for our final answer, we will have 2 ln of absolute value of square root of x minus 1 plus 2 square root of x. And with that, we can now combine all of the terms together, giving us with x cubed over 3 ln of x minus x cubed over 9 plus 5x over 128 plus sine cubed 2x over 48 minus sine 4x over 128 minus sine 8x over 1024 plus 2 ln absolute value of square root of x minus 1 plus 2 square root of x. Now, for our bonus problem, we take the definite integral of the equation from 0 to 1. To do that, we just have to substitute 0 and 1 from our equation, or from the integral that we got, which gives us here is our upper limit minus lower limit, substituting their values. However, if you've observed, we have here for our first term in the lower limit an ln of 0. And as we know, ln of 0 is undefined, meaning that our integral is divergent. Thank you for watching this week's SYNThink. For any concerns, please contact any of the personnel below. If you want to take on the challenge for our next SYNThink, do feel free to come by our booth at Velasco Walk during Mondays to Wednesdays and try on to take on the challenge for that 100 peso raffle. Thank you and have a nice day.